Hello everyone, welcome to A+ Physics. I'm Dan Fullerton, and in this video, what we're going to do is we're going to take the 2015 AP Physics C Mechanics exam and go through the solutions to the free response questions. Now as we go through these, I'd like to note that the official solutions, the answers, the scoring guides haven't come out yet. So it's quite likely I may make a couple mistakes in there, happens all the time. Please give me the benefit of the doubt, I'll do my best, but hopefully you should at least get a good idea of how I might go attacking these sorts of problems. So let's start with the free response number 1. Okay, we have a block on a ramp inclined at some angle theta. And we've got a motion sensor there, and it looks like what we're going to do is we're going to take the block with some initial velocity v0 and send it up the ramp. And the first thing we're going to do is find the acceleration of the block, find its velocity, and find its position. Pretty standard sorts of questions. So, as we get started here, let's take a look. Part A1, determine the acceleration A of the block. All right, so for A1, the acceleration of the block, well, we could go through and draw our pseudo free body diagram where we'll have our force of gravity down. And if we're looking for the acceleration of the block, well, we also have the normal force up. But the only thing pulling it down the ramp is going to be this horizontal component of the gravitational force, which is going to be mg sine theta. And since F equals ma, the acceleration we could just write right off the bat as A equals g sine theta. A very common answer in these sort of problems. Now for part A2, determine an expression for the velocity v of the block. Well, for that we can go to our kinematic equations, where our final velocity is equal to our initial velocity plus the acceleration times our time. In this case, our initial velocity is going to be minus v0, the way we've set up our axis here, plus our acceleration, g sine theta, times t. So now we've got A2 velocity as a function of time. For part A3, we're asked to determine an expression for the position of the block. Well, realizing we start at point D, capital D, our position is going to be equal to capital D minus v0 t plus 1/2 g sine theta t squared. Displacement is your initial velocity times t plus 1/2 your acceleration times the square of the time. Just your basic kinematic equations. So that's pretty straightforward. Now let's take a look here at part B. All right, derive an expression for the position x min of the block when it's closest to the motion sensor. Do this in terms of the specific variables and any physical constants as appropriate. All right, well, I would first note that we get to the point x min occurs when v equals 0. So let's solve for the position when the velocity equals 0 using our kinematic equations again. We could start with v final squared equals v initial squared plus 2a times our displacement, delta x. And if we want that final velocity to be 0, this implies then that 0 squared equals our initial velocity, v0 squared, plus 2, our acceleration, g sine theta, times delta x. Solving for delta x then, I get minus v0 squared over 2g sine theta. Now we still have that d factor in there. So this implies then that the minimum position closest to that motion sensor at the highest point on the ramp is going to be capital D minus v0 squared over 2g sine theta. Again, basic kinematics, just coupled with that capital D, which can be a little tricky if you're not looking out for it. Okay, let's go to a new page here, give ourselves some room. part C, we get a couple of axes, and it asks us to sketch the graphs of position, velocity, and acceleration as functions of time as it goes up and down the ramp. And of course, explicitly label any intercepts and maxima, minima, things like that. Fairly common question. Let me grab my ruler here, and we'll make our graphs. So as I look at my first one, we're looking at position as a function of time. What's that going to look like? Well, I would draw it something kind of like that, where we have an asymptote up here at capital D, and we have an asymptote here at x min. Our next graph is velocity versus time. And we're going to start at minus v naught, going to go up linearly because we have a constant acceleration. And if we solve for the time right there, the time when our velocity is 0, t is v naught over g sine theta, just using our kinematic equations. So we could fill in that point too if we wanted to. And of course, we go up here to v naught. And over here for acceleration, acceleration versus time, that's just going to be our g sine theta. So transferring what we already learned into these graphs. For part D now, let's see, the block slides back down, leaves the bottom of the ramp, and slides on a horizontal surface with the coefficient of friction given by mu k. Find an expression for the distance the block slides before stopping. Oh, well, that's a little bit ambiguous. The distance the block slides before stopping, that could mean up, down the ramp, and then over the flat part, or it could mean just once it comes to the bottom of the ramp. And the difference there is just adding in twice the distance it travels on the ramp. I'm assuming what they're actually talking about here is how far it goes once it reaches the bottom of the ramp. So we're going to solve it that way. However, it's quite likely they would probably take both answers to this problem depending on how you interpreted the question. So the first thing we're going to do here is recognize that the force of friction is going to be mu times the normal force. And since it's sitting on a flat surface when we're on the bottom, the normal force is going to be equal to the weight of the box. So the force of friction is mu mg. Acceleration is force divided by mass. Our mass isn't changing, so that works. Force over mass is just going to give us mu g. So when I want to find the distance that this is traveling, d equals vf squared minus vi squared over 2a, again using our kinematic equations, which is going to be equal to v naught squared over 2 mu g. And there we have part D. And finally, part E, the ramp now has friction. We're going to take the same block, project it up with the same initial speed, and let it come back down the ramp. Now we're going to draw the velocity as a function of time for this new situation. All right, and I don't know exactly how much detail they're looking for, but let's see what we can do here. For part E, something like this, where we've got time, we've got our velocity, and they label points TF over 2 and TF. Well, once again, we know the initial velocity down here, it's minus V naught. And as we travel, this time when we have friction up there, we're going to hit zero velocity before we reach TF over 2. So I would draw it like this, and then our slope's going to shift a little bit as we go off like that. So you could go in a little bit further and put in more detail if you wanted, find some other points, spend a lot more time on it. But given that we're after doing this with the limited time span, getting as many points as possible, I would probably just stop there and go on to the next question. So we'll call that the end of question 1. Let's take a quick break. We'll come back to question number 2. And we're back with question number 2. This looks like we've got a variation on a ballistic pendulum. We're taking a small dart, launching it at an angle of 30 degrees above the horizontal with an initial speed. It's going to hit a block hanging by a string. It's going to cause it to displace up at an angle, and it's going to rotate back and forth like a pendulum. So part A, determine the speed of the dart just before it strikes the block. Well, to do part A, to determine that speed, we recognize that at its highest point is a projectile in a parabolic path. All of its velocity is going to be horizontal, which is going to be the same horizontal velocity it was launched with because there's no horizontal acceleration in this problem. Therefore, v initial in the x direction is just going to be our initial velocity, 10 meters per second, times the cosine of the angle it's launched at, 30 degrees, or 8.66 meters per second, which is going to be the velocity at the top of its path in the x direction, which is also just the velocity at the top because there's no y component of velocity there. So 8.66 meters per second would be the answer to A. Now for part B, find the horizontal distance between the launching point of the dart and a point on the floor directly below the block. Okay, well now what we're going to do is we're going to figure out how far it travels horizontally by figuring out how long it's in the air before its y component of velocity is 0, and then we can use that to figure out the x component of its velocity. So I'll start by writing what we know kinematics-wise in the y direction. The initial y is 10 meters per second times the sine of 30 degrees, or 5 meters per second. The final in the y direction is going to be 0 meters per second, and the acceleration in the y direction, the acceleration due to gravity, we'll call 10 meters per second squared down, or in this case, minus 10 meters per second squared. So solving for the time it takes for that to occur, v final in the y direction equals v initial in the y direction plus acceleration times time. Therefore, our time is v final in the y direction minus v initial in the y direction, all divided by our acceleration, or 0 minus 5 meters per second over negative 10 meters per second squared. 5 over 10, that's just 0.5 seconds. Once we have that, we can find the distance it's traveled horizontally. Delta x, or displacement in the x direction, is just going to be v initial in the x direction times time. We said the initial velocity in the x direction was 8.66 meters per second. Times our time, 0.5 seconds, is just going to be 4.33 meters. All right, we're on a roll here. Part C, find the speed of the block just after the dart strikes. Well, that looks like a great case for applying the law of conservation of momentum. Conservation of linear momentum, I should say. Be a little bit more specific here. And as I do that, I'm going to use a momentum table to do that just because it helps me organize my thoughts. So we'll have for part C, we'll have the momentum in the x direction before the collision in kilogram meters per second, and the momentum in the x direction after the collision or the event in kilogram meters per second. And our objects include our dart, the block, and we'll put a row here for total. All right, and initially, our dart has a mass of 0.02 kilograms, and it's traveling 8.66 meters per second, which gives it a momentum of 0.1732 kilogram meters per second when I multiply that, the mass times the velocity. The block is at rest, so 0, and our total momentum in the x direction before the collision is 0.1732 kilogram meters per second. After the collision, the block and the dart stick together, so they have a combined mass now of 0.12 kilograms, and we don't know their final velocity, so their momentum after the collision is their combined mass, 0.12 kilograms, times this unknown v. So our total is 0.12 v. Now, the law of conservation of linear momentum says without any external forces acting upon them, the total momentum before must be equal to the total momentum after. So I can go and set these two equal and solve for v. Divide both sides by 0.12, and I find that we get a velocity of 1.44 meters per second. Great, we've hit part C. Doing well. For part D, calculate the angle theta through which the dart and the block on the string will rise before coming to rest. All right, well, I'm going to give ourselves some more room for that. This looks like it's going to be a little bit more involved. So as we look at part D, I'm thinking the best way to tackle this is probably conservation of energy. So using a conservation of energy approach, our total energy at the bottom of the path for our dart and block is going to be its kinetic energy, 1/2 mv squared. We'll set that as our zero level of gravitational potential energy. So that's going to be 1/2 times our mass, 0.12 kilograms, and we just found the speed of 1.44 meters per second squared to give us a total of about 0.1244 joules. That's got to be equal to the total energy at the highest point. So the energy at the top is going to be equal to mgh. It stops for a split second at that highest point, so we don't have to worry about the kinetic energy there. So that's going to be equal to energy, I should say E top equals mgh, which implies then that our height is going to be equal to the energy at the top divided by mg, or 0.1244 joules, divided by 0.12 kilograms, and our acceleration due to gravity, I'm estimating that at 10 meters per second squared, to give us 0.104 meters. Now we're going to do just a little bit of geometry and trig. If we want to find that angle, I'm going to first recognize, let's draw a little diagram over here, that when it's hanging straight down, this length is L, the total length of our string. Now when it's over here at this angle, we can draw a little triangle here, recognizing that this is still L. If that's L, this is some angle theta, then this distance right there must be L cos theta, the adjacent side using trigonometry. So then what we're really trying to find here, what we know is this h, which is from there to there, the difference in those two. So as I do a little bit of math here, h must be equal to the total length L minus L cos theta. So I can write that h equals L minus L cos theta. Factor out the L, that's 1 minus the cosine of theta, which implies then that theta must be the inverse cosine of 1 minus h over L, which implies then that theta must be the inverse cosine of 1 minus our h, 0.104 meters, over L, the total length of our string, 1.2 meters, and I come up with a theta, an angle of about 24 degrees. All right, that covers part D. E says the block then continues to swing as a simple pendulum. Find the time between when the dart collides with the block and when the block returns to its first position. Well, if that's the time to go up and back, that's half of the period. So we could find the period, assuming this is a small angle, and 24 degrees is starting to push the small angle approximation, but I think that's what they're after, is us to use the formula for the period of a pendulum. So for part E, I would recognize that the period of an ideal pendulum is 2 pi square root of L over G for small angles of displacement, which will be 2 pi square root of our L, 1.2 meters, over 10 meters per second squared, or about 2.18 seconds. That's the whole period. So the time to go to the highest point and back to where it started is half the period. So t over 2, the time we're after, which is the period divided by 2, half of 2.18 is going to be 1.09 seconds. All right, let's take a look here at F. In a second experiment, a dart with more mass is launched at the same speed and angle. It collides with and sticks to the same wooden block. Would the angle theta swing that the dart and block swing to increase, decrease, or stay the same? Well, I would say that angle is going to increase. As you have a more massive dart, you're going to have more momentum. As you have more momentum transferred to the block, you get more kinetic energy. So you're going to have more gravitational potential energy at the top, and therefore a higher height. More height, more h. Therefore, you're going to have a greater angle. So for F1, I'd say that's a greater angle. For F2, would the period of oscillation after the collision increase, decrease, or stay the same? That's kind of an ambiguous question, and there's a lot more to that question than I think is what is intended by the College Board here, because we're keeping in mind we're at the limit of what we call the small angle approximation, and it really depends on how much more massive that dart is, how much bigger that is. However, I think if we're going to try and keep this simple as just a 1 or 2 pointer as we're finishing off this question, let's go with the simple approximation and say that it's not going to be a whole lot more massive. We're just going to go up a little bit higher, in which case we would say that we would expect the same period. Why? There's no mass dependence in our formula for the period of an ideal pendulum. That's making a couple assumptions and certainly simplifying the problem. But as we're taking a time test, I don't think we want to get into this a whole lot deeper. Let's finish off this problem, go to our next problem, and just keep getting as many points as we can as quickly as we can. So with that, let's take a short break and we'll come back for question number 3. And we're back now with question number 3. Got a uniform thin rod of length L and mass m allowed to pivot about its end as shown in the figure above. Using calculus, derive the rotational inertia for the rod around its end to show that it's ml squared over 3. And how nice they actually give you the answer. If you go back to our previous videos, we actually do this exact derivation as we're talking about moment of inertia. But let's go through it again here, get every point we can on the exam. So for part A, what I would first do is as we look at our rod, we're going to pivot it about the end. Let's set up lambda, a variable, as our linear mass density, total mass divided by the length. Once we do that then, we could say that lambda times L equals the total mass, or the differential. If we chop this up into little tiny bits, the differential of mass, dm, is going to be equal to lambda, the linear mass density, times dr, the distance in the x direction. So now we can solve for the moment of inertia. Moment of inertia is the integral of r squared dm, our general formula for moment of inertia. That's going to be the integral from 0 to L of r squared, and we said dm was, oops, that didn't come out so well. Let's try that again. From 0 to L of r squared, dm is lambda dr. So our variable goes from r equals 0 to r equals L. Now, lambda is a constant. It's a uniform rod, so we can pull that out of the integral sign. So this becomes lambda integral from 0 to L of r squared dr. And the integral of r squared with respect to r is just going to be r cubed over 3. So this implies then that our moment of inertia is going to be equal to lambda r cubed over 3 evaluated from 0 to L, which just becomes lambda L cubed over 3. This implies then, though, we said over here lambda equals m over L. So if lambda equals m over L, we can substitute that back in to say we have m over L, L cubed over 3 is our moment of inertia. L cubed over L just becomes L squared. Therefore, our moment of inertia, I, becomes ml squared over 3, which conveniently matches the answer they want us to achieve. So that covers part A. Part B, derive an expression for the velocity of the free end of the rod at position B when it's come from the horizontal all the way down to the vertical. Express your answer in terms of m, L, and any physical constants. All right, this looks to me like another conservation of energy sort of problem. So as we tackle B, we know that the gravitational potential energy at the top point must be equal to the kinetic energy at the bottom point. At the top point, our gravitational potential energy, we'll call that mg L over 2, looking at the center of mass of the rod and how far that's going to move. Calling the gravitational potential energy at its lowest point 0, must equal the kinetic energy, which is now rotational, or 1/2 I omega squared, the rotational velocity. However, we're looking for the linear velocity of the point B at the end. Therefore, we know that omega equals v over r, and our r in this case is equal to the length of the rod, L. We can then state that mg L over 2 equals 1/2 times our moment of inertia, ml squared over 3, times omega squared, which is v squared over L squared. Now we just have a little bit of an exercise in algebra to show that V squared equals 3G capital L, or looking for just V itself, that's going to be the square root of 3GL. And I think we've adequately answered B there. Okay, moving on. Part C, indicate which quantities should be graphed to yield a straight line whose slope could be used to calculate a value for the acceleration due to gravity. Well, if we've got this as V equals square root of 3GL, and we want to be able to find G, we don't want square root of G in here. But what I could do is I could square both sides and say that V squared equals 3GL. So if I were to plot this in the form y equals mx plus b, I would have y, V squared on my y-axis, equals, my horizontal axis could be L for the x. Oops, let me write that a little bit better, a little bit more clearly. X for L, and 3g becomes my slope. So the slope would be 3g if I put V squared on the y-axis and L on the x-axis. So for the horizontal axis, I would plot L, and for the vertical axis, I would plot V squared. So then it says, using the remaining rows in the table, record any quantities you indicate that you would need that aren't there. Label each row you use and include units. So let's do that on the next page here. If we were to draw that table, I would have something that looks kind of like this. Okay, where we have our length, we have our velocity, and we'll have another line down here, another row for our V squared in meters squared per second squared. And the first two are already filled in for you, so we're just going to fill in the blanks down here. How many do we need? 6 of these? 2, 3, 4, 5, 6. That should do it. So our V squareds, I'm just going to take the velocity here and square it. 7.29, 14.44, 21.16, 27.04, 33.64, about 39.69. So there's the data I would use for this graph. Now once we've done that, plot the straight line data, label your axes, all the standard stuff. So let's just take a quick break. We'll speed things up here for a second and take a look at our graph. All right, graph done. So as I draw my best fit line here, I notice that all the points line up. We get our nice linear fit, which is what we expect. If it wasn't linear at this point, we'd probably have to check and see if we did something wrong. Now that we've done this, though, it says, using your straight line, determine an experimental value for g. Well, we already said that 3g would be our slope. So our slope is equal to 3g. If our slope is equal to 3g, then g is equal to slope over 3. Our slope then, as I go and I pick a couple points, I think I picked a point right up over here, and I picked another one, looked like mine went through 0, 0. So I picked those 2 points for my slope. That ended up being 36 meters squared per second squared divided by 1.35 meters all over 3. And I came up with the slope. Oops, pardon me, that's not the slope. If it's all divided by 3, what I'm giving you then is g. They said that g was about 8.9 meters per second squared. A little bit less than what we'd expect. So the 2 ways in which the effects of air resistance could be reduced. You could come up with a bunch of different possible answers there, but a few that I would think up off the bat. Number 1, use thinner rods so you have less surface area, less air resistance, less friction. Or 2, why not do it in a vacuum chamber? Remove the air from it. So a couple different answers you could come up with there, but that should get you the last couple points. and hopefully a nice end to this exam. Thank you so much for your time, and if you're looking for more help or more information, come visit us at aplusphysics.com. Thanks everyone, and make it a great day.